Good morning, everybody, and welcome. This is sort of a nice oscillation. I'm actually hoping to see this big Foucault pendulum at the Griffith Observatory in Los Angeles in December. It's planning a big road trip from LA to New Orleans, so trying to get that organized. But because there's a American Association of Physics Teachers meeting in New Orleans happening in January, I'm presenting some research there. But anyway, the idea is that this thing swings back and forth, and it's in a constant plane of swinging. But then what happens is the Earth rotates underneath it once every 24 hours, so you see the thing going around. It seems to, from our perspective in LA, it tends to trace out this big path once every 24 hours, sort of proving that the Earth rotates. So this morning's pre-class quiz, there was an object at the end of a spring undergoes simple harmonic motion. This idea is that when you get to equilibrium of the spring, the force is zero. This is like equilibrium or something like that. F equals zero, so acceleration in the x direction equals zero, but the velocity does not equal zero. And in fact, it's actually at its maximum velocity because it's being pulled towards equilibrium. And as soon as it gets past equilibrium, it's also being pulled towards equilibrium. So if it's going towards equilibrium, it's speeding up. If it's going away from equilibrium, it's slowing down. So the equilibrium position is maximum velocity, but the net force is zero. Object of mass m attached to a spring. The other end of the spring is attached to a fixed wall. When the mass is pulled and released from a distance a from equilibrium, it vibrates with simple harmonic motion. The amplitude is a, and the maximum speed of the motion is v max. If you released it to a from equilibrium, I think what happens here is that the E is equal to 1/2 k a squared, and it's also equal to 1/2 m times v max squared. So I think a is kind of proportional to v max, or a, anyway, the absolute value of these things, because their squares are kind of equal or proportional to each other. And then this one was a bit of a trick question. Is it turns out that a pendulum of length L, I think the period is something like 2 pi. I have to look ahead at my aid sheet here. This is the last thing on my slides. Remember what the period of the pendulum is? It's 2 pi square root of L over G, where G is 9.8. So it doesn't depend on the mass. Even if the mass is doubled, 9.8 meters per second squared. Doesn't change. So good. Someone noticed that on the term test 2 solutions for the written problem, I rounded the answer to 3 significant figures. So that's totally my mistake. I apologize for that. It really should have been rounded to 2 significant figures, I think. But it doesn't matter to the marking. You don't lose marks for rounding to the incorrect number of significant figures, because I don't think it's that important. Why was the jumpy physicist never able to stay put in one position? She had a spring in her step. A nice topical little joke there. Also, someone mentioned that it's Angie's birthday, so there's a dog undergoing simple harmonic motion. Okay. So, I told you last time that one thing that always mystified me was the cosine right in the middle of a mass on a spring question. So I'm going to go through a big, long explanation, and it's going to come all the way around to cosine in the end. So, and it starts with a little bit of review of chapter 2. If you have constant velocity, then velocity is change in position divided by change in time, delta t. And you can rearrange to get the final position. If you know the initial position is equal to v, initial position plus v times delta t. Similarly, if the acceleration of an object is constant, then definition of acceleration is it's a change in velocity divided by delta t. You can rearrange that, and you can get that the final velocity is the initial velocity plus a times delta t. Okay, so that's real basic old stuff. We've got a problem where we've got this mass on a spring, and the net force is Hooke's law. It's negative k times x, and you divide out by mass, and you get this crazy equation. That's what we're trying to solve today. And k and m are constants, but now acceleration is proportional to position. And that's not good, because position is obviously changing with time. And so velocity is going to change with time, and acceleration is going to change with time. So, desperate times call for desperate measures. This is my little thinking, which is that, wait a minute, if you choose a small enough time interval, almost anything kind of looks constant. Like if it doesn't change very much over a little delta t, so maybe we can kind of cheat and use those equations of constant velocity and constant acceleration, but just for a little time, and then we'll kind of divide the motion into segments. We'll just do it again and again and kind of try to step through it. So this is called numerical integration, and people used to try to do this with pencil and paper, but then we made an invention called a computer, and if you think of it, the word computer has a verb in it, which is compute. And so that's actually what you can do with a computer. So we can do this. Here's the strategy. We'll split up the motion of a mass on a spring into many segments, where for each segment, the initial velocity of the next segment is the final velocity of that first segment. And we're just going to keep doing that again. And then also, final position of that first segment becomes the initial position of the second segment. So you get it, right? So, but the thing is, if the acceleration is approximately constant over a small time interval, we're going to use this equation. V final is just V initial plus A times delta t. We're just going to pretend A is constant. And then similarly, if the velocity is approximately constant, we can say the final position is the initial position plus V times delta t. Again, not really correct, but we can pretend V is constant because it's probably constant over a small enough time step. And then once we do that, we can just go to the next segment again and again and again. So let's try it out. So what I have tried doing here, the pink cells on my Google Sheet, want to expand it a little bit? A little bigger here. These are just numbers that I've typed. They're kind of like the input numbers. So time starts at 0, x starts at 1 meter. So what I want to do is take the mass. It's on a spring. The spring has a spring constant of 1 newtons per meter. And on the mass on the spring has a mass of 1 kilogram. I could change it, I guess, if I wanted to change it to different things, but let's just call it 1 kilogram. And then what happens is I started at position 1 meter with speed v is 0, so we're going to release it from rest. And then the acceleration is a function. It's negative f3, which is k, times b2, which is x, divided by f4, which is the mass. So it's negative kx over m. You can see that equation. I've just computed what the acceleration is. And the dollar signs mean that if I copy and paste it, it'll always go from that cell. But without a dollar sign means if I copy and paste, it'll kind of work my way up. So the time is equal to the original time plus f2. What is f2? Oh, f2 is what's called the time step in seconds. So it's plus 0.005 seconds. So if I press Control C and Control V, and Control V and Control V and Control V, Control V, what I'm going to do is just step up the time by 0.005 seconds every time. And then the position is the old position B2 plus C2 times F2. Okay, so C2 is the old speed, times F2. Oh, it's the time step, so that's good. So I've just done V times delta T. So, yeah, V times delta T gives you a new position. And so what I can do is press Control C, and now I get a new position. And the V is the old V plus the old acceleration times the time step. So I'm just updating the velocity by the time step as well, times A. And then the acceleration, you just get it by, this is just negative this, because I think these are ones, but I guess I could change it to some other number. But let's leave it at ones for now. And now what I can do is Control C, Control V, V, Control V, Control V. And what is weird is that if you just look very, very carefully over here, see this tiny, tiny, tiny little blue line? I'm making a graph of x versus time. You have to have super good eyesight to see it. You see it? This is going to take forever. But I can do more than one paste at once. Control V. So you can see the x is kind of decreasing with time. And so I guess I can just keep going here. Let's do Control C and just highlight a bunch of cells. Control V. And so the first 2,000 steps look like this. Okay, so this is the surprising result. And what's funny too is that it goes to its maximum negative position at pi seconds, 3.14 seconds. This is actually a weird way of computing pi. It tends to overshoot a little bit, I think, because I'm not doing my numerical integration very well. But it's a nice smile, looks like cosine. That's where this thing comes from. So I think the important thing to remember is that we've just done Hooke's law and stepped through it, and somehow we got cosine. So this is a motivation for that function, which is in our slides here. This one. We think that it seems like a mass in a spring goes like this. It's a mathematical model of motion. Okay. So this is a different kind of top hat question I'm going to give you. And I don't actually know if it's going to work. Well, let's see what it looks like. Because I don't know what it looks like from your end. You're supposed to match things. So there's the equation. It's x equals a cosine brackets 2 pi over capital T times lowercase t. So all of these things in that equation are either variable, meaning they change with time, constant, meaning that they don't change with time, or I guess there could be something in there which is a function, which is a function takes one number and converts it to another number based on some sort of rule. So you might be able to grab these things on the right and kind of shift them up and down so that they match. So then at least 3 of them are constants, 1 of them is a function, and 2 of them are variables. Constant doesn't change with time, variable does change with time, and a function is a function. Like it changes one number to another. Can you slide it up and down? No, I think you just move it, but up and down only. Yeah. So they stay on the right. You don't try to move them to the left, just up and down. Okay. It's fun with top hat, so. I'll give you 60 seconds, I guess. It's working. Tomorrow we can sleep. Okay, hopefully you've been able to line them up with these categories and submit. And we'll okay, let's see here. I don't know what it's going to show. Okay, so it shows the answer. So I think, yeah. Basically, x and t are the variables, and because they change with time. A and pi and capital T are the constants, and cosine's a function. It's just a button on your calculator that changes one number to another number. And it has to be, by the way, in radians to make this whole thing work, as you could sort of see. Okay, thank you for that. Okay. So the idea here is that as the position changes, the force is negative kx. That's, I guess, called Hooke's law, right? For springs. And then, you know that Newton's second law of motion is that acceleration is the net force divided by the mass. And when you combine them, you get this. The acceleration is negative some constant times x. So if you look at the graph, if you notice, it's just flipped upside down by that negative number. When position's maximum, then the force is the most negative, and etc. And there's a velocity somewhere in between. So let's think of this in terms of slope, remember? If I start with maybe a blue graph, like let's say there's the amplitude A. Try to draw this along with me. You've got a curve which goes through 0 and then gets to negative A down here. This is 0, by the way. And it gets to its maximum negative here, then it's going to go through there, then it's going to hit A again. So it's kind of fun to try to draw it. Goes like this. It doesn't go straight down. It passes through the x-axis at kind of a slope and then turns around, goes down. So that if you look at the slope of this, so by the way, this is time versus x. The slope of x versus t is called the velocity, and we'll go to green for that. So v versus t. When it passes through 0 is actually when it's most slopiest. So it's going to be its maximum negative v max here. And then this is its most positive slope right here. So we're going to call plus v max up there. So whenever it passes through the origin is when it's going to have its most velocity. And then actually when it gets to, it's released from rest actually, so that's 0 velocity. And when it gets to its maximum negative position, it stops for a little bit too. So every time it's at its maximum or minimum position, that's when it passes through 0. And now you got to try to draw. It's actually the exact same curve, but now it's like like an upside down sine curve or something. Let's try to draw it. Make sense? And then the slope of velocity versus time curve. Do you know what that's called? Let's use orange. It's called acceleration. And then I guess there's going to be same sort of thing. A max plus A max and negative A max. And so the slopes here, they're going to be 0 at the maximum or minimum of the green thing. So zeros are there. And then it starts with its maximum negative slope, And then when it passes through here, that's its maximum positive slope. And then here, maximum negative slope. And here, maximum positive slope, etc. So you can try to draw that thing. And look at that. Notice how, this is A versus time. Notice how the orange curve on the bottom is the upside down of the blue curve on the top, just as we expected from Hooke's law, which is the force is equal to negative k times x. So the acceleration is negative k over m times x. And k over m is a positive number, so you'd expect the orange curve to be the flipped upside down of the blue curve. So again, it's all kind of motivating with calculus how this works. Okay, now we're going to do another top hat question, and it's based on the next slide. So focus on the next slide for a second. The period t is set by the properties of the system, and we have a bunch of demos set up to show this. In this case, in the case of a mass m attached to a spring of spring constant k, the period is always t is equal to 2 pi over the square root of m over k. But the amplitude of the motion is set by the initial conditions. So what are we trying to do again? Remember, we are trying to describe this equation. X is equal to a times cosine of 2 pi over t times t. So there's two, pi doesn't change, it's just pi. But a and t are constants that have something to do with the motion. Different oscillators will have different amplitudes, different periods. But the period is set by the conditions of the system, the mass and the spring constant, and the amplitude is set by the initial conditions. So let's do another top hat question. The question is, which of the two constants of this motion, a or t, in the description of simple harmonic motion, is determined by the initial position and velocity of the mass? Remember, the variables here are x and t. I guess they're lowercase, and the constants are a and capital T, uppercase. Think about that. Pair up with your neighbor, share your answer. Make sure you're all voting the same way. Click in, please. Survey says. See if you guys are following me here. You got 73%. I likey. So that's the amplitude is set by that initial kick. But the period is not. The idea with the period is that it's going to be the same no matter what the amplitude is. Surprisingly, it's the properties of the system. So if we actually try to test that, I got these. Now, these are vertical masses on springs because they're just a little easier to set up because we don't need a frictionless surface. But here we have two springs that are identical, and we have two non-identical masses. So m is higher, and it's, what is it again? 2 pi. Period is equal to 2 pi square root of m over k, right? So if I hang this mass on this spring, whoa, it goes way down here to equilibrium. So the equilibrium is actually interesting too. It's when the stretch of the spring times its spring constant equals mg pulling it down. So for a smaller mass, actually doesn't go down as far. The delta, the x is a little less for this one. Anyway, that's equilibrium. So now we're going to pull them away from equilibrium and release. Oh, and that's got a much shorter period because mass is less. Okay, smaller mass, shorter period. Okay, but I guess the idea is that if I change the amplitude, it'd speed them up, but they go farther, but the period is still the same, surprisingly, for each one, right? And then, what's the other one doing here? The other one is they're the same mass, but they're different spring constants. So I've got, whoa, this is like a low K spring and a higher K spring. So if you hang this mass on here, it has to stretch it quite a lot until it comes into equilibrium because this K is low. And that's in the denominator, right? And then this one, same mass, it only stretches it about this much. So you release these. And the higher spring constant has the lower period, because it's 2 pi square root of m over k. Oh. This sounds like my stupid be real notification. I'm totally deleting this one after the semester, I think. Anyway. Okay. Also, I'm deleting Snapchat after this semester. Some of this social media I just can't get used to. Okay. But I like Insta. That's a nice one. Okay. Let's go back to laptop 2. So, and then there's this comparison in the textbook, which I don't know if this is helpful to you. It's not very helpful to me, but I'll just show it to you anyways, because it's in the text. Yep. Had send to hell? Thank you. Good. It's a comparison of uniform circular motion to simple harmonic motion, which is simple harmonic motion. I'll draw that first, because that's what we're doing, which is that you've got a mass and a spring. Here's a mass. And you set up you define your origin x equals 0 to be at the equilibrium position, and there's x. We know that a sub x is equal to negative k over m times x. So we also know that 2 pi over the period is equal to the square root of k over m. And so what you get is that the acceleration in the x direction is negative 4 pi squared over t squared times x, the way the constants all work out. And the trial solution here is just that x is equal to a times cosine of 2 pi over capital T times t. Okay. So then I want to talk about uniform circular motion. So you've got some object, which is, here's the y-axis, here's the x-axis, and there's an object here at some angle theta, and we'll call the radius of this circular motion a. Radius is a, and the object moves with constant omega, or I guess I'll call it angular velocity, omega in radians per second. Radians per second. So I think theta final is equal to theta initial plus omega times t. That's from your equations of constant angular acceleration. Actually, it's the equation of constant angular velocity. And you can also set theta initial equals 0, so it starts on the x-axis. So if it starts on the x-axis, then theta is equal to omega times t. And also, do you remember that omega is equal to 2 pi over the period for constant uniform circular motion? So you've got theta is equal to 2 pi over t times t. And then there's a triangle. I told you triangles were going to come into this at some point. Here's theta, here's y, and here's x, and here's a right angle. And here is the radius, which is a. From here to here, that's the hypotenuse. So the cosine of theta is equal to the adjacent divided by the hypotenuse, which is equal to x divided by a. And so solve for x. X is equal to a times cosine of theta. But then we have theta. It's up here, so we can plug it into there. Get x is equal to a times the cosine of 2 pi over capital T times t. Whoa! Exactly the same. Okay, so So this is, I don't know, one of these tricks. I don't know where the heck this all comes from, but the idea here is that mathematically, simple harmonic motion is exactly the same as looking at something in uniform circular motion from the side. I'm not quite sure why this is. It's a little surprising, but there you go. This is the same as this. This was the trial solution that came out of nowhere. This was just doing a triangle. Anyway, physics just never ceases to amaze me. So. Okay. All right. Times it. 740. Doing all right? Okay, good question. What are V max and A max? So if you've got a position function, which is given by this, then it turns out that, so basically, this is my thing. My thinking is this. Cosine is a function, and its maximum is 1 and its minimum is -1, is a function which it kind of sloshes between, goes between +1 and -1. So that means that x max is equal to A. Make sense? Must have bumped it or something. Okay. And then same kind of thing is that this thingy right here goes between, sign goes between +1 and -1. So V max is going to be equal to 2 pi A over capital T. And similarly with this, these, so basically sine and cos are between, always between -1 and +1. So I would say A max is equal to all this stuff, 2 pi over T squared times A. So that's the answer to that question. What else? Let's do another one with the top hat. Send it to you. This is called the Body Mass Measurement Device. There's a photo of it up there on the International Space Station. So astronauts have to do a lot of work to keep themselves in shape because otherwise their muscles atrophy. And so they like to know what they weigh. But you can't just step on the scale because there's no normal force in space. There's gravity still on you, but there's nothing pushing back. You're just floating around there. So what they do is they sit on a springy chair and measure the period. So the chair without anybody in it has a period of 1.2 seconds. If she sits in it, what will be the new period? Think about that. Share with your neighbor. Make sure you agree. Just 20 seconds to click this in. Okay, and then shift it when we go to another one. Okay, yeah, sounds good. Okay, let's do. Survey says. Yeah, it's going to be more. Basic idea there is just that, remember that period is equal to 2 pi times the square root of m over k. So if m goes up, then is that right? m goes up, then the period goes up. Okay, good. All right, so if I want to do this, probably can. Here's this body mass measurement device chair. Has some mass of the chair, is 32 kilograms. Has a vibrational period of 1.2 seconds. And when the person, the chair and the astronaut are together, there is a new period of 2.1 seconds. And the question is, what's the mass of the astronaut? So first of all, I'll start with a system, which is the chair plus the spring. And then we've got a wall somehow. It's like the side of the space station. Here's the spring constant K, and here's the mass, mc. And then we're going to change the system to the chair plus the spring plus the astronaut. So the spring stores potential energy, basically, which we'll talk about in a bit. Here again is the wall. That's important to give it that momentum. Then there's K, and now we've got mc plus ma is the new mass there. And so this oscillates with some period tc, and this oscillates with some period tca. And so t is equal to this 2 pi times the square root of m over k. That's the equation we're going to use today. System 1, we can solve out. So system 1, this is our strategy. Solve for k, which we don't know. And then system 2, solve for m sub a. We're going to plug this into here. So I know that Tc is equal to 2 pi square root of mc over k. So I can square both sides. And every time there's a square root on one side, I have to solve it by squaring both sides of the equation. And I get that k is equal to 4 pi squared mc over tc. And then system 2, the tca is equal to 2 pi times the square root of mc plus ma all over k. Square both, well, divide by 2 pi, get tca squared over 4 pi squared is equal to mc plus ma divided by k. And I can rearrange that, find mc plus ma is equal to k over 4 pi squared times tca squared. And actually, k over 4 pi squared just equals mc over tc. So I'm going to plug that into here, and I get mc plus ma is equal to mc over tc times, oops, there's a squared here, sorry. There's a squared there and a squared there. Tc squared over tca squared. Okay. So the mass A is equal to the mass of the chair times tca squared divided by tc squared minus mc. So I get 32 times 2.1 over 1.2 squared minus 32. I get 66 kilograms. Something like that. Is the mass of the astronaut. Something like that. Okay. So I alluded to energy. The idea here is that anytime you stretch a spring, it contains potential energy, and it's part of your system. And then anytime a mass is moving, that contains kinetic energy. So if you look at the energy of vibrational systems, they make this little chart here where they think about this mass going back and forth, and they look at, well, at different positions. So if it starts off at negative A with zero kinetic energy, the elastic potential energy is 1/2 Ka squared. Wait, the clock reading is kind of weird here. But its total energy is 0 plus the 1/2 Ka squared, and you just get 1/2 Ka squared. And then as it passes through zero displacement, that's when it's going its maximum speed. So its kinetic energy is 1/2 mv max squared, but its elastic potential energy briefly goes to 0. So what's happening is that as it moves, the elastic potential energy and the kinetic potential energy sort of slosh back and forth. And there's a graph here of it, which is the green curve is supposed to be, let's go to green here. This is K, which is 1/2 mv squared, not v max squared, but just v squared, because v changes with time. And the blue curve is u sub s is 1/2 K times x squared. And again, x and v are variables here. So you get these nice curves. But when you add them up, you get either this one or this one. And someone asked about this on the pre-class survey this morning. Hello, Mr. Professor. in the textbook, the energy formula for an object going through simple harmonic motion is 1/2 Ka squared. And this is tripping me up a bit. What is the A supposed to be? Is it the maximum amplitude or just an x position? So what it is it's the maximum value of x. Because x is varying smoothly between plus A and minus A, right? So, but the issue here is that when x is at its maximum position, that's when it stops momentarily. It's the turning point, right? It was going to greater and greater x, and then it comes back again. So when it does that, it turns around, it has to have v is 0. So if v is 0, then the kinetic energy at that moment is 0. So the total energy at that moment, which is kinetic plus this potential, it's just all the potential. So the elastic potential energy at x equals A just happens to be the total energy of the system. So it's a nice little trick to find this total energy. So you can find Vmax actually if you rearrange all this stuff. You know that 1/2 Ka squared equals 1/2 mv max squared. So you can rearrange that and get the Vmax is square root K over m times A. And that kind of makes sense because if you got a larger mass cart, it moves more slowly. And if you got a stronger spring, it's going to kind of speed it up. Okay. Do a couple of quick top hat questions. By what factor must we increase the amplitude of vibration of an object at the end of a spring in order to double its maximum speed during a vibration? What are we doing again here? So this, I think, is actually asking about maximum speed. It was way back here. I went through it kind of quickly. It was this one. Vmax is equal to 2 pi A over T. So let's go forward again. Okay, this one. Vmax, give you 60 seconds. 2 pi A over T. And the other equation, I guess, is that T is 2 pi square root of m over K. Check your neighbor, make sure you got it. Okay, survey says increases by 2, right, because it's proportional. The Vmax is 2 pi over t, so that's constant, right? This is fixed by the properties of the system. Fixed. Assuming it doesn't change mass or spring constant, you're not changing t. You're just doubling A, you're going to double Vmax. So next question is, by what factor must we increase the amplitude of vibration of an object at the end of a spring in order to double the total energy of the system? So there's 2 equations for total energy. You can use E total is equal to 1/2 m times V max squared, or another one, and I'll put both of these on your rate sheet, E total is equal to 1/2 k times A squared. Either one works. You want to use the amplitude one? Might be right. Yeah, so sort of makes some sense, right? If we double the amplitude, the total energy is going to go up by a factor of 4. So I think you're looking, you can't double it, you want to do less than doubling it, right? Okay. I'm going to give you some more time to click that in. But basically, the next thing I wanted to do quickly is talk about pendula, and we're going to go over this table next time, but the condition for simple harmonic motion for mass on a spring is you do have to have sort of small oscillations because Hooke's law has to be obeyed. If you overstretch the spring, you won't have simple harmonic motion. There's also something called a pendulum, and that has a period 2 pi L over G. So just real quick, we'll be done here. The idea, 2 pi L over G, if it's got a longer length, then it has a longer period. You kind of see that. This one takes longer to swing back and forth than the shorter length pendulum. But what's interesting too is that it doesn't depend on mass. 2 pi L over G, where G is just the acceleration due to gravity. These had the same length. Release them from the same distance. Let them go. And they swing with the same period, even though they're much different masses. So the mass doesn't come into it, and we're going to try to prove why that is when we come back on Monday. Child swings in a swing, then a child sits, the swing oscillates back and forth with a certain period. If she stands up, how does the period change? Talk about that. Have a great weekend, everybody. I'll see you Monday morning.